Okay, in this video we're going to be talking about motion in a plane. We're also going to be talking about vectors. But for now, let's just talk about motion in a plane. So let's say we know something's position, which we signify in math S of t, and we know its position at any time is given by this equation t cubed minus t. So, we know what that graph looks like. It's a cubic. It's got zeros at, let's see, -1, 1, and 0. So we start off negative position with a positive velocity. We reach a maximum distance, local max, and then we have a negative velocity, local min, and then a maximum velocity. And these zeros are when we're at our origin. If I wanted to find my velocity, well, I'd take the derivative. We'd get 3t squared minus 1. And that corresponds, if this is my position graph, my velocity graph is a quadratic. It's going to look something like this. And it makes sense as far as our graph is concerned. And we can think about that in terms of this. Everywhere where I've got a negative velocity, where my velocity is decreasing rather, my function is concave down. And everywhere where I have an increasing velocity, my function is concave up. And let's see, anywhere where my velocity is positive, I'm going to be going in the positive direction. So, or rather, my function will be increasing. And anywhere where my velocity is negative, I'm going to be going down, have a decreasing function. So that's how those all interact. And lastly, we know that for acceleration, that's just the derivative of the velocity, 6t. And so my acceleration is positive as long as t is greater than 0. And we've got a slope of 6. So we're going from a cubic to a quadratic, down to a linear function as we take our respective derivatives. Okay, well, in order to model this, we're going to be using vectors. And what vectors give us, they give us two things. They give us both direction and magnitude, magnitude being size. So what we want to talk about right now is how do you name a vector, and the idea of splitting it up into x and y direction. So when we name a vector, this vector we're going to call u, and the vector is given in terms of its x coordinate, which we're going to call a, and its y coordinate we'll call b. So really, any coordinate is just given, any vector is just given in terms of its x length and its y length. So therefore, this is going to have length a, because that's my x value, and this here will have length b, because that's my y value. And the notation, these greater than less than signs, that's just the notation that says my vector u is composed of a x length of a and a y length of b. Okay, what can we do with vectors? Well, the first thing that we're going to talk about is that we can add them. So we're talking about vector addition. And the symbol is kind of strange. We've got two vectors, u and v, and we want to add those vectors. So it sort of looks like a bullseye. But the main idea is that when you add vectors, you just add the x coordinates and the y coordinates. So given some vector 3, 4, if I wanted to add that vector 3, 4 together with the vector 1, 2, this is going to equal a new vector 3 plus 1, comma, 4 plus 2, which is the vector 4, comma, 6. Well, what does that look like graphically? We're actually going to spend a bunch of time in the multivariable portion. But as far as graphically what we're talking about is we've got a vector 3, 4. Here it is. That's 3, 4. So here's my vector u. And then on top of that vector, I'm going to draw, so tip to tail, that's something you've probably heard before. From the end of that vector, I'm going to draw my new vector, which is, length 1 up 2. So that looks like this. And when I sum those vectors, the vector is just the old end to the new tip, which is that line right there. And the y values have a length of, well, the first length was 4, and the next length was 2, so the total length is 6. And the x values were 3 and 1, so their length is 4. And that's where the 4 and the 6 come from. Let's look at another example of that. So let's imagine that we've got, and this will be easier to see, let's say that we've got the vector let's say that we have the vector 3, comma 4 and negative 2, comma negative 3. We want to add these vectors. Well, we have 3, 4, so there's my first vector, which is 3 and 4. And then my new vector, this one here, says go down 2, so I'm going to go down 2, and then over negative 3. So that's this distance here. Oh, I think I said that wrong. Hold on a second. Let me re-say that. So we had 3, 4. Yeah. And then my new vector goes negative 2 to the left and 3 down, which gets me to this point. So my net vector, the sum of those vectors, is the following. It's the old end to the new tip, which is right here. And if we think about that addition, it's 3 plus negative 2, comma 4 plus negative 3, which is the vector 1, comma 1, which is what we have. 1 by 1. What about multiplication? Well, for now, we're only going to be talking about scalar multiplication. And scalar multiplication is when you take some vector u, and we're going to multiply it by some constant value r, where r is some number. So what does this look like? Let's say r equals 2, and u equals 3, comma 7. Well then, if we had 3, 7, and this is u, what would RU be? Well, RU is just multiplying each one of those terms, the x and the y, by the amount, in this case 2. So 2 times 3, comma, 2 times 7, which we get as 6, 14. And so all that does is it takes our vector and it multiplies it by twice as much. So I'm going to add kind of twice as much to my vector, twice the length, and each one of the respective sides is twice as much. So this becomes 6 and this becomes 14. So the scalar multiplication allows us to just increase the size of a vector by some given radius or amount. Now we have two very important vectors, which are called the unit vectors. And unit vector means it has length equal to 1. And these particular unit vectors, the unit vector I and the unit vector j, well, I is just all in the x direction, and j is all in the in the y direction. So the unit vector I just looks like this. It has a length of 1, whereas j looks like that with a length of 1. And what I and j allow us to do is it allows us to take any vector and write it in terms of I and j. So what we can do is we can take this negative 3 comma 7 and split it up into its x and y components. So we could think of it as the sum of negative 3 comma 0 plus 0 comma 7. Well, and then we could think of multiplying. Here what we're doing is we're doing scalar multiplication, so we could think of negative 3 comma 0 as negative 3 times 1 comma 0, and 0 comma 7 as 7 times 0 comma 1. And then we can replace those vectors with the standard unit vectors. And that becomes negative 3i plus 7j. And so it's just a helpful way for us to write vectors when we start thinking about putting them into their respective components being x direction and y direction. So if I wanted to write the following in terms of I and j, take a second to do that, and then maybe pause the video and then see if you got it right. The first one is just going to be 2i plus 5j. And the second one, 3i minus 2j. Yep, it's as easy as it looks. So if we look at the first one, that's saying 2 in the x direction plus 5 in the y direction. This is 3 in the x direction minus 2 in the y direction. Not too hard. And what about the length? Well, the length of a unit vector, is just basically we're using Pythagorean theorem. So imagine, this has length a and this has length b. Well, this is going to be the square root of a squared plus b squared, using the Pythagorean theorem that a squared plus b squared equals c squared. And just as far as a definition goes, when we talk about length of a vector, given the vector u, in shorthand, we write that the length of vector u equals the absolute value of u. And the absolute value means get rid of the direction. And like we saw before, it's just doing the Pythagorean theorem. So let's first find the length of this vector 3 comma 4, and then let's find a unit vector in the same direction. So just before we move on, remember a unit vector has length equal to 1. Well, what about my vector 3, 4? What's the and notice I'm writing as the absolute value of, well, that equals the square root of 3 squared plus 4 squared, which is 5. That's its length. So this has a length of 5. But if I want to be in the same direction as that, so 3, 4, so if I want to be in the same direction, but with a length of 1, so in other words, you know, a fifth of this length, what could I do? Well, I could write, what I can do is I can take my unit vector and just divide it by its length. And that will get me a unit vector in the same direction as my original vector. So for this particular problem, we're just going to take 3, 4. We're just going to take 3, 4 and divide it by its magnitude, which is going to give us the vector 3/5, 4/5. Okay, the way, let me stop for a second. So now we have some function r of t, and r of t is the sum of two functions. And it's the sum of a function that all in the I direction plus something that's all in the j direction. Now, hold on one second. Okay, so when we want to talk about, sorry about that, when we want to talk about the domain of a function, we know that as far as ln t is concerned, because we know ln t looks like this, the domain for ln t is that x must be greater than 0. And if we look at 1 minus t, in this case, it's a graph that looks like this. No. I think it looks like this. In this case, we know that t must always be, or our domain is that t must be less than or equal to 1. And I should be talking about t here as well. So what's the domain of the following function? Let me just make sure that I've done that right. I feel like I have. If I graph the square root of 1 minus x, yeah. So what's the domain? Well, the domain is the intersection of the respective domains. So I know that my first one had a domain of that t needed to be greater than 0, and here t needs to be less than or equal to 0. So my total domain of this function is that the domain is that t must be less than or equal to 1, but greater than 0. And that would be my total domain of this function, because it is the intersection of the respective component domains. Okay, so this problem has to do with us thinking about some vector addition as well as what the standard unit vectors are. So in A, it says u plus I. Well, u is negative 1 comma 2, and I is 1 comma 0. So that vector is going to be 0 comma 2, which is going to look like this, straight up in the y. So length of 2 in the j direction. And B says u plus j. Well, same idea. Negative 1 comma 2 plus j is 0 comma 1. So the resulting vector is going to be negative 1 comma 3. And so that vector is going to be negative 1 in the x, 3 in the y. So it's going to look something like that. Just to highlight it, make it a little bit more clear. The vector we're talking about is right here. Okay, what about the other ones? Let's put them on a different page just so it's a little bit easier to see. So in C, I have u plus I plus j. Let's get out of that pen. So u plus I plus j is negative 1 comma 2 plus 1 comma 0 plus 0 comma 1. And we just add each of those respective values together. Right here, we're doing this one here. So we end up getting negative 1 plus 1 plus 0 is 0 comma 3. So this is 3j. That's how we can simplify it, and it just is a vector that has a length of 3 all in the y direction. Negative j, what's that going to look like? Well, negative j is just negative 0 comma 1, and then we can distribute that negative across, which is 0 comma negative 1, which will look like this, going down with a length of negative, well, the length is still 1. The negative is the down part, so it has a length of 1. And last but not least, if we do E, it's 2u minus 2j, so 2 times negative 1 comma 2 minus 2 times j, so 0 comma 1. So when we do this work, we get negative 2 comma 4, and then minus, distributing that in, 0 comma 2. And so now we're subtracting these vectors. Again, we're doing this problem here. So that's going to be negative 2 comma 2, which we could write as negative 2i plus 2j, and it's going to look like this. 2 to the left, 2 down, and the resulting vector is that. Okay, so let's just quickly kind of scroll through what we talked about. First, we talked about, there's motion in a plane, and we can model that motion in a plane by position, velocity, and acceleration. And we quickly moved on to say, okay, we're going to be using vectors. So clearly, we didn't do much of this, but we're going to be using vectors to describe motion in a plane. And so we have this new idea, vectors, and vectors have direction and magnitude, and we write them in the following way. And we've got, the x component and the y component. And we can add vectors like we did here. Oh, and we add vectors tip to tail. And then we can multiply vectors by a number. And then we have these standard vectors, I and j, which have length 1, which means they're a unit vector. Standard, meaning that I goes in the x direction. So the I is going in the x direction, where the j is going in the y direction. And then we can express any vector in terms of I and j, and that was a really easy process for us. Make sure that I remember what I was doing there. What else did we do? We talked about length of a vector, expressing vectors as a unit vector by dividing by its total length, domain of vectors, and lastly just did some vector addition and using arrows to represent them. So that's vectors.